thank you to the organizers for inviting me to give this talk. Is a lot of fun. And I'm very happy to talk about this topic, which is relatively new research on flat origami crease patterns. So I want to introduce what face flips are and talk a bit about why they are interesting, why we might care about face flips in flat origami, and then show you some new results that all of which I think are maybe 3 years old or less, so relatively new work. So here we go. So we're talking about flat origami crease patterns. So I always think of them as a graph with vertices and edges, V and E. A straight line planar graph drawn on a piece of paper, P, which is a subset of the plane. But we also have a valid mountain valley assignment, which we can think of as a mapping from the edges, our crease lines, to -1 and 1, where -1 means mountain and 1 means valley, or something like that. Okay, so we have a flat foldable crease pattern and a mountain valley assignment that that is valid meaning that it will fold it without the paper ripping or anything. Then here's what a face flip is. A face flip is a new mountain valley assignment that we get by switching all the mountains and valleys about a given face. So given a face F of the crease pattern, a face flip of F under a mountain valley assignment mu is a new mountain valley assignment denoted mu sub F that equals the original mu mountain valley assignment, except being reversed on the creases that border F. And here's the technical definition. You basically just change the sign of all the creases, the mountains and valley assignments of the creases that border F. Okay, so we should look at some examples and see what like so here is the classic square twist crease pattern. With the bold lines are mountains and the lighter lines are valleys. Okay, so here's a face F1, and I could flip that face, and so I do that, and I do that in this picture down here. So all the mountains and valleys have been flipped about F1, and that turns out to be a good crease pattern. This will also fold flat. Okay, then I could flip F2, and that gives me this crease pattern. So this changes the original. This is the classic square twist crease pattern where we have mountains bordering the center square, the center diamond, and it turns it into this iso area square twist that is pretty well known. But then look what happens when I flip F3, this face down here. That gives me this crease pattern, and this is not a valid mountain valley assignment. Okay, mainly if you look at the vertex that adjoins F3, it now has 2 mountain creases across this 45-degree angle, whereas the 2 neighboring angles are 90 degrees, and you can't have that. That is not flat foldable. It violates something called the big little big theorem. So you can't just flip every face and still get a valid mountain valley assignment, and that is one of the challenges with face flips. So we call a face flippable under a mountain valley assignment mu if mu sub F is a valid mountain valley assignment. So if we can flip a face and still have a valid mountain valley assignment, we call that a flippable face. And so this is just a close-up of that vertex that I showed you before, illustrating which faces are flippable. Those have check marks, and the non-flippable faces have little do not, no signs in red. And the reason why these 2 faces are not flippable is because if you flip them, they will violate the big little big theorem that says if you have a small angle in a flat origami vertex bordered by bigger angles, then they cannot, the creases surrounding the smaller angle cannot be the same. They cannot both be valleys or both be mountains. Okay, so if you flip either of these 2 faces, that will give you either valley or mountain there, and that's no good. So we can label all the faces that are flippable or not flippable to see how these face flips work. Okay, so that's a start of an introduction. But why are face flips interesting? I think they're interesting just because they're nice, and you'll see they lead to some interesting mathematics. But they also have been interesting to some physicists, and physicists in particular, actually. this is where I first got the idea, was talking to physicists. In particular, I collaborated on a paper with Jesse Silverberg and some other people. This is in 2014, where we looked at the Miura-Ori crease pattern. And the physicists were interested in introducing defects into the mountain valley assignment of the Miura-Ori as a way to change its flexibility. They were viewing the Miura-Ori as a metamaterial, and they wanted to change its Poisson ratio, or its resistance, by literally doing a face flip. They talked about it as popping the vertices up and down, but it amounts to basically a face flip. So these pictures are a little hard to see, but here they're taking this, which one is it? I think it's, yeah, I think it's this parallelogram here that I'm trying to highlight with my mouse pointer. And they're moving these two opposite vertices, and that's doing the same as changing all the mountain valley assignments about that. And you can still then recollapse the Miura-Ori, but one of the faces now has been tucked underneath other faces. And that locks a certain part of the Miura-Ori. And so it's no longer as flexible as it was. In this paper, we talk about how we can use moves like that to program how much resistance the Miura-Ori has as an expanding and contracting mechanism, or as a metamaterial. So that's one way in which face flips can be used to directly change the mechanical behavior of an origami model. But also there was a paper in 2018 by Michael Assis that uses face flips to study the statistical mechanics of some origami tessellation patterns. And I was surprised to see that, but that's a very nice paper, looking at origami tessellations, like very large origami tessellations with lots and lots of creases, and almost viewing them as a molecular structure. So you can study its thermodynamical behavior and look for phase transitions. That's what statistical mechanics does. But to make that work, to make the math and the physics work there, they had to, Michael had to employ face flips as a way to examine relationships between mountain valley assignments. And that's one of the things that face flips really allows you to do. So, and that leads to this thing that I like to call the origami flip graph. Okay, so here, this is a way to visualize how face flips react with one another, okay, and change a mountain valley assignment. So we create a new graph. So given a flat foldable crease pattern C, we define the origami flip graph, which I call OFG of C, as a graph whose vertices are all the valid mountain valley assignments. Okay, so you take every single valid mountain valley assignment, they create the vertices of this new graph. And then two vertices in this graph, which corresponds to valid mountain valley assignments, we connect them with an edge if there's a single face we can flip to go from one to the other. Okay, so here's an example. We'll just take this degree 4 vertex with 45, 90, 135, and 90 degree angles. And we already saw that only 2 of the faces are flippable when we do this, faces 1 and face 3. So we can take this mountain valley assignment, and I drew that as a vertex over here in the origami flip graph, that same. So here I'm decorating the vertices with the mountain valley assignment so that you can see which vertex corresponds to which mountain valley assignment. But this is really just a vertex. And then I can flip face 1, and that gives me this new mountain valley assignment where I've just changed the mountains and valleys about the 45 degree angle. Okay, or at this original one, this upper left corner, I could have flipped face 3. That would turn these 2 mountain creases into 2 valleys. So I get that mountain valley assignment. From that mountain valley assignment, I can flip face 1 again to get this, and then I can flip face 3 again to get up here. And this gives me a 4 cycle. And these are the only 4 valid mountain valley assignments of this vertex. So this is the complete origami flip graph of this vertex. And I like this. This is a nice way to visualize how the different mountain valley assignments that are valid, how they relate to one another with face flips. It gives us a nice picture, or even a configuration space if you want to use fancy words, but it gives us a nice picture, a nice way to visualize the mountain valley assignments. So the goals of this talk with that introduction is to the following things. I want to present new research that has been done on origami flip graphs and face flips in particular. I want to first start with looking at the structure of the origami flip graph of C, where C is a single vertex crease pattern. So like the example we just saw, but what happens if we get to more of them? So we'll look at that a little bit and look at origami flip graphs for single vertex crease patterns. But then we're going to look at a particular single vertex crease pattern, which I call A sub 2n, which stands for the vertex of degree 2n. So 2n creases coming out of a vertex with all equal angles around it. That's a very nice case and has some interesting mathematics to it. And then I will end with a summary of some work that I've done with a bunch of people on larger classes of crease patterns, in particular some origami tessellations, and what do their origami flip graphs look like? What can we say about them? So we'll start with single vertex crease patterns. And I need to say that this is work I did with some students of mine at a summer program called Mathily Est, which is a research experience for undergraduates. And it took place at Bryn Mawr College, which is near Philadelphia. And the students I worked on here were Natalia Tersakov, Sarah Nash, and Manuel Morales. They were from, they were 3 undergraduates from different colleges. Natasha was at the time was at MIT. Sarah Nash was at New College of Florida, and Manuel was from Arizona State University. And this happened in 2019. Now Natasha is a graduate student at Rutgers University. And so I had them look at face flips of single vertex crease patterns. They found a lot of conjectures, and we managed to prove some things. And so that's what I'm going to show you. But this has been ongoing work since then. So some of the work that we've done, some of the proofs we have are very recent. Yes. So one of the first things I want to do with single vertex crease patterns is to contrast them with something, because origami flip graphs can have a lot of variety. So this is just a simple example. Imagine a piece of paper that's a rectangle with just 2 vertical creases like this, where faces 1, 2, 3 are squares. The origami flip graph for this is actually the graph K4, the complete graph on 4 vertices. And that's because you can flip any of the faces, and this will still be foldable. And so for example, if I flip face 1, that just changes that crease. And if I then flip the face 2, I'll move over here. So, but I'm showing this example to show you that origami flip graphs can have 3 cycles in them, or even be a whole complete graph where that is a graph with all possible edges. That can happen. But single vertex crease patterns have a lot more specific structure, and that makes them an interesting place to start examining this. So our first theorem that we proved was that if your crease pattern C is just a single vertex crease pattern, SVPC, single vertex crease pattern, then the origami flip graph will always be bipartite. And that means it has no odd cycles. So here's the proof of that. It's not a very hard proof. It's kind of fun just to see how we would do something like this. So I let C be a flat foldable single vertex crease pattern, okay? And then I look at the origami flip graph, and I imagine a cycle in it. Every cycle in the origami flip graph is a sequence of face flips, say, which I call A, and maybe the faces are F1, F2, F3, up to Fk, okay? And that will start with some mountain valley assignment mu, and then change it, and then come back to mu. So it's changing a mountain valley assignment and then bringing it back to the same mountain. That would be a cycle in the origami flip graph. Okay, so, but our crease pattern is just a single vertex crease pattern here. So what are the possibilities? Well, one possibility is that our sequence of faces contains every face of the crease pattern C. That case is quite a bit different than if some of the faces are missing from the sequence. So we'll treat them as 2 cases. So in this case, if every single face is flipped here, but maybe some of them are flipped twice, you can flip a face more than once. And in different orders, that might do different things to the mountain valley assignment. So I define some notation here. I say let n of alpha be the number of times face alpha gets flipped in this sequence A. okay? Because like I said, a face might be in the sequence more than once. So for a given face alpha, let n of alpha be the number of times we flip it. Then now every crease CI must be switched an even number of times. That's because we're starting at a mountain valley assignment and coming back to the same mountain valley assignment. So each crease might change, but it must change an even number of times to come back to where it started. And that means now crease CI is only changed if we flip the two faces next to it that I call alpha I and alpha I plus 1. So that means if I sum n of alpha I and n of alpha I plus 1, that must be an even number, right? Because that way crease CI will not be changed. All right, so that's true. So therefore, if I look at the size of my sequence A, okay, remember I'm trying to prove that this is an even cycle. Okay, so I'm looking at the size of this cycle in my flip graph A. The size of that will be the sum of the number of times each face appears in that sequence, and that's what n of alpha I is. So just add up all those things for all the faces, and that'll give us the size of A. But then I could split that sum up into pairs of adjacent faces and add those up. And each one of those is an even number because each crease must be switched an even number of times. And this is the sum of a collection of even numbers, and therefore must be even itself. So that shows that the size of A must be even in this case. And that means this must have been an even cycle in the origami flip graph. Okay, so that is this case 1. Case 2 is, well, suppose some face of the crease pattern alpha I is not in A, my sequence of face flips. If that's the case, then the next face, so alpha I is not flipped. Then the next face next to it, alpha I plus 1, must either not be an A as well, or it must be an even number of times. And that has to be true so that, again, the crease between these two faces gets flipped, gets changed an even number of times, and therefore comes back to where it starts after doing A. Because remember, this is a cycle in the origami flip graph. So if alpha I is not an A, then the next face must be an A an even number of times, or not at all. And the same thing then must be true with the next face and the next face and the next face. So that means every face that is in A must appear there an even number of times, and therefore the A is even as well. And so that means this is also an even cycle case. So those are the only two possibilities. So that's it. So these origami flip graphs are always bipartite. Now let's look at some more examples, because that's an abstract theorem, but it doesn't mean much if you don't have anything to picture. So we already saw this first example of here in this example, let's look at degree 4 flat foldable vertices. There's only 3 types that we really need to look at. One we already saw, where we have a smallest angle, and then its neighbors are bigger, and we had a 4 cycle for that origami flip graph. But what about this crease pattern? This is sometimes called the bird's foot. It's also the vertex and a Miura-Ori crease pattern, where you have 2 equal small angles and then 2 larger obtuse angles. And this is interesting because whether a face is flippable or not depends on the mountain valley assignment. That did not happen with this previous case. Here, these 2 faces are never flippable, no matter what, because they violate the big little big theorem. But here, it's a little different. If we have this crease pattern where we have 3 mountains there, and then 1 valley in between, like the middle toe of the bird's foot, then every face is flippable. So that vertex is going to be degree 4 in the origami flip graph. But if instead we have only, say, this right toe of the bird's foot is a valley and the others are all mountains, then 2 of the faces will not be flippable. That's because, like this small face labeled 2, we can't flip that because then we'd have 3 valleys for the toes and a mountain for the heel of the bird's foot, and that doesn't fold flat. That's not a valid mountain valley assignment. Same thing here. If I flipped face 4, then I'd have 3 mountain toes and a valley for the other crease, and that is also not a valid mountain valley assignment. So this mountain valley assignment has only 2 flippable faces, so it is of degree 2 in the origami flip graph. Oh, wait, that's over here, this one. Okay, and so if you go through the 6 different mountain valley assignments here, you get this pattern with its origami flip graph, which I think is kind of interesting. But then there's this case, which I call A4. This is the all equal angle case. Here, every angle is 90 degrees. And for this vertex, we could flip any face, and like every face is always going to be flippable. So every vertex in the origami crease pattern has degree 4. And there are 8 valid mountain valley assignments of this. So we get this very nice symmetric looking origami flip graph here, where again, I've labeled all the edges by what faces you're flipping to get from one to the other. So that makes you think that there might be some nice, pretty graphs that we could get from these origami flip graphs, especially in this case where all the angles are equal. That has the most symmetry of this. But unfortunately, if we go to a degree 6 vertex, things get more difficult. So here is, so because these cases are interesting, I let A sub 2n be the vertex with 2n equal angles. That's the all equal angles case. That's why I use the letter A for A sub 2n. Here's the graph we just saw before, where we just have 4 creases, all 90 degree angles. But if you have 6 creases with all 60 degree angles, well, that origami flip graph will have 30 vertices, because there are 30 valid mountain valley assignments of this. And that's a very large graph. Here I'm only showing half of it. And the challenge with this is that we no longer have the case where every face is always flippable. So like here, all the vertices were degree 4, because no matter what I do for the degree 4 case here, any face can be flippable. But here, things change. And I try to illustrate this down here. If I have a mountain valley assignment like this, with these 2 mountains and the rest valleys, then I could flip any of the faces and it would give me a valid mountain valley assignment. But if my 2 mountains are next to each other and the 4 valleys are down here, then I cannot flip the face that is bordered by the 2 mountains, because then I would have all valley creases, and that violates Maekawa's theorem. You can't do that. So this vertex has degree 5 in the origami flip graph, whereas this vertex has degree 6. And so so you start getting vertices of different degrees in this case. It'll still be a rather symmetric graph. So this is only half of the origami flip graph. Here are just the vertices that have 2 mountains and 4 valleys. There's another isomorphic copy of this that is 4 mountains and 2 valleys, but then they interconnect in some way, and so it's a little bit hard to visualize, but it's still kind of a nice graph. But that made us think that maybe this case is interesting to look at. And there was another thing with that. Okay, so my students decided to focus on this a little bit, and they discovered this, which I think is a rather nice theorem, that if you take any flat foldable single vertex crease pattern, not necessarily all equal angles, but just give me any single vertex flat foldable crease pattern of degree 2n, then its origami flip graph is going to be isomorphic to a subgraph of the origami flip graph of the all equal angles case. This means that the all equal angles case is kind of a mother graph for all the origami flip graphs of the same degree. And I'm not going to prove this because it's a little bit technical to prove, but it makes a lot of sense if you think about it, that when you have all equal angles, you have the fewest constraints on what faces are flippable and what faces are not flippable. If you start changing some of the angles, make some of them smaller, that removes some vertices from your origami flip graph. There's some crease patterns that are no longer valid, that were valid in the all equal angles case. And so therefore it removes some edges too. So you get a subgraph. So here I've tried to draw these, the bird's foot and then this other vertex. So you can see that their origami flip graphs are really subgraphs of the all equal angles case. So that again makes this all equal angles case an interesting case to explore, which is what I want to do in the next few slides. So we discovered a bunch of things about the all equal angles case. And first of all, we were able to prove that the origami flip graph in that case is always connected. That is not always true about single vertex crease patterns. They're not always connected graphs. Sometimes they're disconnected, and that's another thing that's kind of interesting. And they have diameter n. The diameter of a graph is the number, the length of a longest path in the graph. Like how far away can can two vertices be from one another? It turns out that the diameter of that graph is n. Those aren't too hard to prove, but I want to focus on counting the number of vertices and edges in the origami flip graph, because that's one of the first things you do with a graph is see, can you count the number of edges and the number of vertices it has. The vertices are easy to count. It's just Miyazaki's theorem. And the all equal angles case, if it's degree 2n, you're going to have 2n, say, mountains and n-1 valleys. So that Miyazaki's theorem is true. So 2n choose n-1 is the number of ways you could pick the valley crease, like n-1 valley creases from 2n creases. But then that's if you have more mountains than valleys. So you can then switch them all. So you multiply by 2. So this is how many vertices this graph will have. 2 times 2n choose n-1. Okay. But the number of edges was really difficult for us to figure out. I mean, we had these examples that we looked at, but it wasn't, it was hard for us to see a pattern in them. And it was really hard to draw some of these graphs when 2n started getting large, like even 8 was very difficult to draw the origami flip graph. So we wrote an algorithm to count the number of edges in the origami flip graph. And it's not a very efficient algorithm, unfortunately. It was a very slow algorithm, but it got the job done. And it was actually not hard to implement on Mathematica, it turns out. The way we do it is we make a list of all the valid mountain valley assignments. Just make a big list of them. And there is actually a way to do this relatively easily on Mathematica. So we put them all in a set called MVs. All right. And then for every so these represent all the vertices in an origami flip graph, right? So for every vertex, if it's majority mountain, then we calculate it's the degree it will have, which is exactly 2n minus the number of VV faces, the number of faces that are bordered by 2 valleys. So if it's mountain, if it's majority mountain and we have a face with 2 valleys next to it, we cannot flip that face. So that is one face we can't flip. All the other faces we will be able to flip. So you look at how many VVs there are in that mountain valley assignment, subtract them from 2n, that'll be the degree of that vertex in the origami flip graph. And then you do the same thing with the majority valley things. And then the edges will be the sum of the degrees divided by 2. And that's a standard graph theory result. That the number of edges is the sum of all the degrees in your graph, but then divided by 2. But this is not an efficient algorithm. And so we weren't able to generate a lot of data from it. I mean, unless we let our computers run for a long time. Here's some of our data, though. That first degree 4 graph we saw had 16 vertices. The degree 6 case, all equal angles, had 84. And then it grew very quickly, 400, 820, 8,064, and so on. We entered this sequence into the online encyclopedia of integer sequences, and that sequence is not there. So this was not a known sequence, unfortunately. And so we did not have an easy way to find a formula for it. But we did get a nice table of the degree sequence too, because this algorithm computed the degree sequence for us as well. So we could say that, oh yeah, in the degree 6 case, we'll have 12 vertices of degree 5, 18 of degree 6. And these numbers were very mysterious to us as well. We couldn't really figure out a formula for them. So remember, these were students I worked with during the summer of 2019. And over the next couple of years, we kept working on this. We didn't find a formula for this then, but eventually we were able to. We were able to calculate that these numbers that we see here in this sequence, 16, 84, 400, and so on, actually, this is the formula for them. And we were only able to figure this out by doing a probabilistic proof. And I believe this is the first time I've seen a probabilistic proof in flat origami theory. So I think this is kind of interesting. And so I'm going to go through the proof because it's rather nice. So, and if you're not familiar with probabilistic proofs, this will be exciting, hopefully. So here's what we do. We're going to count the number of edges in the origami flip graph by using probability. We define a random variable G, which is the number of flippable faces in a valid mountain valley assignment chosen uniformly at random. Okay, so pick at random one of the mountain valley assignments of A sub 2n. the all equal angle case. Okay, and we're going to ask what's the probability that that it will have, say, 3 or 10 or whatever flippable faces. Okay, so in other words, G is the number of good faces, faces we can flip. We're going to let B be the number of bad faces, faces we can't flip, the unflippable faces. Okay, so then we're going to do a trick here. What we want to do is analyze this probability, and that will lead us somewhere good. So I create an indicator random variable called one sub alpha I, that is the random variable for alpha I being a bad face. So this will be 1 if alpha I is a bad face, and 0 if alpha I is a good face. Okay. Then we can, our goal is to compute the expected value of this random variable G, the number of good faces. Okay. We're going to compute this in 2 ways. All right. So the first way, for the expected value of G, which you can think of as like the average value of G over the whole probability distribution. Well, G is really 2n minus B, right? 2n is the number of faces, and B is the number of bad faces. All right. So G is 2n minus B, and B is really the sum of these indicator random variables, telling me like 1 if it's a bad face and 1 if it's a good face. So if I sum those up, I'll just get the number of bad faces. Now, what's nice about the expected value is you can, and it's standard in probability courses, is that the expected value is linear. So you can move it inside the summation here and pull the 2n outside. So so the expected value of G, the random variable G, is just 2n times the sum of the expected values of all these indicator random variables. But those are just all the same, because this is a symmetric all equal angle case vertex. These expected values will all be the same, and they'll all equal the probability that alpha I is bad. Okay, so we've really just got to compute this. What is the probability that a specific face is bad in this probability distribution? And that is something that we can actually figure out. So here we do. So here we go. We're going to figure out what's the probability that a given face is bad. Well, if the face is alpha I, then let's call its creases on the left and right of it EI and EI plus 1. Okay, so let's suppose that this vertex is majority mountain. Okay, I don't have to do well. Anyway, the alpha I will be bad if its 2 neighboring creases are in the minority case. So if they're valleys, if it's majority mountain, because that means you'll get rid of 2 valleys and you'll no longer satisfy Maekawa's theorem. So what's the probability that these 2 creases are minorities? Well, that's equal to the probability that EI and EI plus 1 are valleys, and the mountain valley assignment that we're looking at is majority mountain, or those 2 creases are mountains, and the mountain valley assignment we're looking at is majority valley. That's the 2 cases that could happen. Okay, and each of those 2 cases are equivalents, because we have just as many majority mountain valley assignments as majority valleys. So this is equal to 2 times just one of them. Say EI and EI plus 1 are valleys and mu is majority mountain. So what's that probability? Well, that probability is, this is the intersection of 2 events, 2 probabilistic events. So we can use conditional probability to calculate that. That'll be equal to the probability that U or mu is majority mountain, just straight out majority mountain, times the probability that EI and EI plus 1 are valleys, given that U or mu is majority mountain. That's just a conditional probability formula that I'm using there. And now this first probability is easy. Because there's half of the crease pattern, half of the valid mountain valley assignments are majority mountain. So the probability that mu is majority mountain is just 1/2. Okay, because they're half of them are majority mountain, half of them are majority valley. And then we have this. And so the 2 and the 1/2 cancel out. That's lovely. And then this is something we can actually calculate. The probability of an event given some other event is just the size of the given event. That's in the denominator. So how many mountain valley assignments are majority mountain? Well, 2n choose n minus 1. That's how many mountain valley assignments are majority mountain. So that goes on the denominator. And then how many ways how many of those mountain valley assignments have EI and EI plus 1 being valley? Well, you make EI and EI plus 1 be valleys, and then you have 2n minus 2 creases left, and n minus 3 of them the other ones have to be valleys in order for my Ikawa's theorem to hold. So this is the probability of this last event, and that's the probability that face alpha I is bad. And if you calculate that, you actually get this number. If you do the n choose k factorial stuff and have things cancel, this is what you get. Okay, so going back to quickly the previous slide, we got that the expected value of G was 2n times 1 minus the probability that a given face is bad. So the expected value of G is 2n times 1 minus this fraction that I just calculated. That is one formula for the expected value of this random variable, counting the that's like, counting the number of good faces in a sense. Okay, but now we're going to calculate expected value of G in a different way. A second way to calculate this expected value is basically using some graph theory techniques that G is the number of good faces. That's going to equal the degree of, say, a random mountain valley assignment in the origami flip graph. That is the relationship between the number of good faces and the degree of a vertex in the origami flip graph. Okay, and now we're talking about a graph, and that's lovely because the expected value for the degree of a vertex in a graph is basically the average degree that you have in a graph, which is the sum of all the degrees divided by the number of vertices. That's the average degree. But the sum of the number of degrees in a graph is 2 times the number of edges. That's what we want to find. We want to find the number of edges in this graph. We know the number of vertices. We calculated that before. That's just 2 times 2n choose n minus 1. So we can take this, since this is also the expected value of G, we can set that equal to the formula I got on the previous slide, and solve for E. So here I put E on one side, and 2 over V turns into this. And then this is the formula that I got before. And V, remember, is 2 times 2n choose n minus 1. That's where the 2n choose n minus 1 here comes from. The 2's cancel. You bring this 2n inside and get a common denominator, and then it'll end up canceling with that 2n, and the numerator turns into this. So this is how we get this formula. And I like this because this is using these probabilistic proofs, which is kind of fun. But yeah, that gives us this nice formula. Now, we were also able, after doing that really got us going. And so then we were able to, and I'm not going to go through this proof very much just because of time, but that allowed us to get a formula for the degree sequence. Like, we can calculate exactly how many vertices of what degrees they're going to be in the origami flip graph too. So this gives us a lot of information. The proof of this is kind of fun too. It doesn't use probability. It just uses the fact, and I'm just going to go through this really quickly. It just uses the fact that that if we want to count the number of mountain valley assignments of a certain degree, well, actually, because I want to do some other things, I'm just going to go through this. I'm just going to show you the pictures here. What we can do is, if we know there's going to be n plus 1 mountains, well, then what we want to do, and suppose it's majority mountain, then what we want to do is keep track of how many valley-valley pairs we're going to have, okay? And we can do that by placing boxes. Imagine we're putting boxes between, like, so I arrange the mountains in a ring with spaces between them all. And then I imagine putting some boxes between some of them, okay? And then in each box, I want to put one valley and then any other valley. So that guarantees that I have like a certain number of valleys being placed. But then whatever, any valleys I have left over will go into one of these boxes now, and that allows me to calculate or keep track of how many valley pairs I have. And if you keep track of what, then this turns this problem into a standard combinatorial problem so I'm skipping a lot of details there, but this you could actually kind of figure out, but with straight combinatorics is the moral there. So the last thing I want to mention is, well, what about bigger crease patterns? Because that you know, so I summarized some of the results we have for single vertex crease patterns. There is some other stuff I did with those students, but what about bigger crease patterns? So in 2018 at the Bel Air's computational geometry workshop, I worked with these people: Hugo Akitaya, Vida Desmojic, David Epstein, Kijit Jain, and Anna Libu on this problem. We specifically looked at origami tessellations. And are there types of origami tessellations where we can say something about what faces can be flipped when and so on? And what was surprising was the variety of structure we found in their origami flipped graphs for origami tessellation. So for example, square grids, that's a type of origami tessellation. So imagine your crease pattern is just a square grid. It turns out that if C is a square grid, then if we focus on locally valid mountain valley assignments, because there is this problem of layer ordering and global flat foldability that is very difficult, as many of you know, I'm sure. So if we just restrict ourselves to locally valid, that means we want Miyakowa's theorem to be satisfied at every vertex. Okay, then the origami flip graph will always be connected, and we can always flip any face. In fact, so we'll always be able to find a way to flip some mountain valley assignment like this to another one like that, no matter what. We can always do that. That's what it means for the graph to be connected. And we can, in linear time, find a sequence of face flips to do that. That's what these pictures are demonstrating. Basically, we look at like the symmetric difference between the two mountain valley assignments. And that gives us a set of these purple dots we could flip to turn this into that, or these teal dots we could flip, and they're kind of like complements to each other. But I'll skip the details there because they're in a paper that came out for this. But square grids were pretty easy to understand. Everything, you can always flip every face, no matter what, and we can always go from one crease pattern to another. In contrast, this origami crease pattern that are called Huffman grids, these are origami tessellations that are made by these kite shapes that are two 90-degree angles and then two supplementary angles. You can tile those, and that always gives you something that you can fold. Here's a picture of me trying to fold this on Mathematica. And if you ignore self-intersections, they will all fold flat. They will all fold a little bit, but then they might self-intersect if your paper's too big. It turns out here that no faces are flippable. All the faces are non-flippable, and the origami flip graph has no edges. This is the exact extreme of the square grid case, where all faces are flippable and and the flip graph is connected and stuff. Here, nothing works, and you can see that. Like if you look at, like, for example, this is a typical mountain valley assignment for the Huffman grid, and if I take this face F and flip it, then I immediately get contradictions with the big little big theorem on the adjacent faces at these vertices V1 and V2. And every mountain valley assignment will have that problem. Every valid mountain valley assignment will have that problem. Every face will have that problem. There's none of the faces are going to be flippable. And so that's kind of weird, but true. What about square twist tessellations? These are a very popular type of origami tessellations. Well, actually, we already looked at this case. We saw the square twist and saw that it has these non-flippable faces and these flippable faces. Here, the cyan or blue faces are the flippable faces. And if you make a square twist tessellation, those are the only faces that are going to be flippable. So you get these nice pictures telling you what faces are flippable. But you can summarize it by saying that, yes, the origami flip graph here will always be connected, and the only flippable faces will either be the trapezoids or the parallelograms, depending on how you tile the square twists in these two different ways that are possible to make a regular tiling. So that's pretty easy to understand. And we can flip from one to the other in a very easy ways because we just focus on the parallelograms or the trapezoids. The Miura Ori, that's a little bit more interesting. Here, we can also prove that the origami flip graph is connected, but it was much harder to do that, and also to prove that we can always find a minimum length path between two vertices in polynomial time. This took a little bit of work that David Epstein helped a lot with in turning this problem into a different graph problem that there already was a polynomial time algorithm for. The challenge here is that you can start flipping some faces, but you quickly run into faces because of, as we saw, each vertex here is a bird's foot. And we saw there in that case that, like, I think here we could flip any face and it'd be okay, but then that will make some other flip faces not flippable. And that's where it gets a little bit harder. Okay, but still we can prove that we can still take the mirror Ori and flip it to any other locally valid mountain valley assignment, which is useful. That meant that the work we were doing with the work I was doing with the physicists back in 2014 means that we won't get into dead ends necessarily. There aren't things that we can't get to by face flipping. We can get to every, at least locally valid mountain valley assignment. The most interesting case the hardest case we looked at were triangle lattices. Here it turns out that, again, if we restrict ourselves to locally valid mountain valley assignments, then yes, the origami flip graph is again connected, but it is much harder to find a minimum path between two valid mountain valley assignments. That this turns out to be an NP complete problem or NP hard. So it's and this is I believe Hugo Akiyata came up with the bulk of this proof. And he did it by reducing this problem to the K vertex color problem, or K vertex cover problem, which was known to be NP complete. So that was the reduction we used. So that's the so here's a table that summarizes kind of the different origami tessellations we looked at to show the variety of what goes on. That the square twist, the square grid, every face was flippable and the origami flip graph was connected. But with the Huffman grid, no faces were flippable and it was maximally disconnected. But with the square twist, well, half of the faces are flippable and it's connected. But with the mirror Ori and the triangle lattice, it really depends. It's hard to predict when faces are going to be flippable or not without looking specifically at, like, well, what do you have happening with the mountain and valley assignments for a specific case by case. So you can figure it out, but you have to look case by case. But their flip graphs are connected. But then as far as complexity, in terms of going from one flip graph, one vertex of the origami flip graph to another, and what faces you have to flip to do that. For the square grid, we can do that in linear time. Square twist, we can do it in linear time. The mirror Ori, it's polynomial time, a little bit harder though. And for the triangle lattice, NP hard. So lots of variety of complexity and structure in the origami flip graph going on here. That is what this is demonstrating. And this is all that's really been studied about this. There are lots of other origami tessellations, but they haven't, I don't know of anyone who's extended this yet. This paper, well, I'll show you in the references, this paper came out in 2020, I believe. So relatively new stuff, lots of more stuff to do. So here are my conclusions. I find just from the stuff I showed you, but there's also more, that origami flip graphs offer a great way to visualize the relationship between mountain valley assignments. It gives you a way to look at structure between mountain valley assignments, and that might be something that could lead us to a greater understanding of flat foldable crease patterns. And even for single vertex crease patterns, and even just in the all equal angles case, origami flip graphs are surprisingly complicated. It requires some reasonably sophisticated mathematics just to figure out how many edges they have and things like that. And for larger crease patterns, we see wildly different behavior in terms of the structure of the origami flip graph, how complicated it is to figure out how to flip from one crease pattern to another. Yeah, so that is basically it. Here are the only two references on this so far, though one of them is a preprint. We're trying to get this paper published now. And since these are students, some of them are still undergraduate students, I'm keeping hold of this until the paper gets accepted for publication, but it's out for review. We'll see, hopefully soon. But for people interested, this paper, but with the people from the Bel Air's Computational Geometry Workshop, appeared in the Journal of Combinatorial Geometry in 2020. there's the link to it. It's available online. It's open access, so it's relatively easy to find. So with that, I'm going to end my talk. Thank you very much for your attention. I hope my English was understandable. And yeah, thank you.
Thank you very much, Tom. That's a great talk. So please give us questions. 質問を皆様どうぞQ&A か。じゃあ上原先生お願いします。
Good morning. Good evening for you.
Thank you. Yes, good evening here. Yes.
Yeah, can you see the how may I say the last summary slide?
Okay. Yeah, sure. The this slide, this one.
This one. Yeah. The last one seems to be the how may I say recently in Japanese theoretical computer science, we are interested in the reconfiguration problem, and the last one, triangular lattice sounds something like such a reconfiguration problems. And yeah, my question is that you show that connectivity of the graph and the NP hardness of the finding the minimum shortest path between them, and between them we have some kind of problem which asks you how can you find the real path connecting?
Yeah, minimum path. Yeah.
Yeah, not minimum path. I mean the path. Can you find a real sequence of triangular lattices between given two configurations?
But not necessarily minimum, just any path.
Any path.
Any path. Yes, we can, because and that was in the proof of the connected case. So the way we do that is we picked a canonical crease pattern, a canonical mountain valley assignment. I think we used one that was like all vertical mountains and then everything else a valley. And so we found a way to take any other locally valid mountain valley assignment and flip it to that canonical one.
I see.
And then from the canonical one, we could go to any other one. So it's not an efficient way to do it, but it will show that we can go between any two. Yeah.
The length is a polynomial.
Yeah, I think so. Yeah, I think so. Polynomial in terms of like, say, the number of triangles, I think, or something like that. Yeah.
If you can say that the NP hard can be said to be the NP complete because the Yeah, I see.
Yeah. Yes. Yeah, I should have put NP complete here, probably. Yeah. Yeah, let me make sure, because I think that was the theorem. Yeah, the theorem was that it was in, yeah. So.
Oh, okay, I see.
But yeah.
Okay.
Yes.
Thank you.
Other question. So I was quite interested about the ones that are disconnected, like the Huffman Grid.
Yeah.
So is there other property of the graph that is known for any patterns, such as, for example, the degrees for each vertex? It's very hard to imagine if it's odd number or if you have some node vertex that is connected, like degree 1 vertex. Do you have any kind of result about the property in general?
Yeah, I think that's a good question. So one thing I didn't have time to talk about in this talk was something else I did with these students here. Let's see. That is, yeah, like for general single vertex crease patterns. When is the origami flip graph connected and when is it disconnected? That's something these students, I guess technically they have a conjecture for it. We have most of a proof, but it isn't quite done yet. And that is very difficult to get a handle on. You need to look at these, because imagine this crease, this vertex was like degree 20 or something like that. Then you could have a lot of different types of angles surrounding it. Some of them might be equal, some of them might be really small, who knows? In order to figure out what the origami flip graph of that looks like, you need to fold it recursively. Like look for a smallest angle and fold that, and then look at the next smallest angle and fold that. And in some of those situations, I'm trying to think that you can, I don't think we've ever found say a vertex of degree 1 in the origami flip graph when doing that. So I think that's impossible, but I don't know of a proof yet. And I would think that would be something. Yeah, what?
Kind of disconnected one for these.
Oh yeah, but some of them are disconnected. Yeah, I don't have a picture of that in these slides, but for example, if you imagine, say, I think a degree 6 vertex, where you have a really small angle over here and a really small angle over there, and big angles in between them. Then if you do it out in just the right way, you can flip some faces, but they won't influence the others. And so there's no way to kind of like, get from some mountain valley assignments to some others. I know that's not very convincing, but we did find examples where it's not connected for a single vertex. And especially it has to do with whether certain big things are nested inside each other. There's things that can happen like that. Yeah, I don't know. I'm teasing you. I'm sorry, and not giving you.
Yeah, well,
but I'd be happy to talk about you with this more later if you wanted. I'm hoping we will have another paper out soon that talks about that, because it's really interesting, but the proof isn't quite done yet. So.
Great. Thanks. I have a question from the audience. First one, it's hard to, it's in Japanese. So does that, is saying is one space and 1 point, one vertex corresponds, or, so I think it was about the graph vertex, I believe.
The origami flip graph vertex. Each vertex corresponds to a valid mountain valley assignment. So that's why I was trying to draw the pictures like this, but I don't know if that's what was being asked.
Yeah, I don't know if that was. There is another question.
Yes, I see that. Viewing A sub 2n as case as a terminal object, can the single vertex case be described as a category? Oh, that's maybe, yeah. That's what I would love for this to turn into, that whenever in mathematics we can take and like explore structures like this. The origami flip graph gives us a structure that we can put onto mountain valley assignments. And then the challenge is that a structure that we already understand elsewhere in mathematics? So yeah, if we can think of the single vertex case as, yeah, some kind of like fundamental building block here, or as you say, a terminal object, then there might be a way of looking at this stuff categorically. I don't think we're there yet. There's a lot of nitty-gritty stuff or details that we don't understand yet, but it would be nice if we could put flat origami mountain valley assignments that are valid into like a bigger mathematical theory. I would love that. And I would love for this to go in that direction, but we'll see. We'll see.
Next question. So I think that's about time for us. So thank you very much again, Tom.
Yeah. Thank you. Thank you everyone for listening.